Excuse me. All right, I will begin. You guys ready? Sorry I'm running late. I just have a hard time getting down here in time. You know? Let's see here. Anybody not have their test 2 back? No? Okay. I think everybody who's here has been here before, usually. And here is the attendance sheet. It's the 30th, right?
Anywhere else?
Here, Mia, I'll let you. You want to check it, and then I'll move it on. There you go. All right, I'll begin with a word of prayer. Ahem. Heavenly Father, we thank you for this day. I thank you for this class, for the students, for their camaraderie. Help us to have a good class today. Help us to glorify what we do and just learn more about exponential functions and all that, Lord. In your name I pray, Lord Jesus. Amen. Okay, so let us begin with I was going to say a definition, but first I had to clean this board. What a mess. It's bugging me. So, part of the reason that some of you have this class is that you're going on to take physics or other science classes perhaps, or calculus. And one of the big players in all those games is the exponential function. We just find exponential functions in all kinds of stuff, like population growth, radioactive decay, all kinds of other biological models, and physical models. Like exponentials come up all over the place. And exponentials fall outside the scope of what we've done so far. So we're really starting something new today. And here's the definition. The exponential function base a greater than 0 has formula f of x equals to a to the x for all x in the reals. In other words, that's the formula. All right, so wonderful. And let's just take a few minutes and graph the case. And the number is called the base. All right, base. So let's look at base 2. Example 1. Let's study f of x equals to 2 to the x. So I make a table of values. Got my x here, got my 2 to the x over there. And let's start at like -3, then -2, then -1, then 0, then 1, then 2, then 3. All right, I'll fill out this table here. What is 2 to the -3 equal to? See, we've thought about this, right? This is really 1 over 2 to the 3, which is also known as 1/8, right? What happens when we plug in -2? Well, we get 2 to the -2, also known as 1 over 4, right? What's 2 to the -1? That's 1/2, right? What's 2 to the 0? Just 1, right? By definition, it's 1. What's 2 to the 1? A very silly way to write 2, right? What's 2 to the 2? 2 times 2, also known as 4. What's 2 to the 3? It's 8. So, with all of this in mind, we can make a graph of this thing. All right? And so the graph let's put some points down here. What are the points on the graph? We got the y-intercept is 0, 1, right? Then when you get to 1, it's up here at 1, 2. When you get to 2, it's at 4, right? When you get to 1 minus 1, you're at a half. When you get to minus 2, you're at a quarter. When you get to, all right, so there's minus 3, minus 2, minus 1, 1, 2, 3. Where is 3, 3, 8? Oh. Tell no one. That doesn't come off. I know, because my children have colored on latex wall paint before with these. It doesn't come off. You can scrub it, but you just scrub the paint off with it. Oh man, I didn't even put it in the right place either. Oh. And I can't fix it. All right, well anyway, you get the idea. I can't even draw that point. It's too high up there, isn't it? Okay, so this is 2, 4. This point, 2, 1. All right, this point over here, minus 1, minus 1/2. All right, and then over here, minus 2, 1/4. All right, enough. So there's y equals 2 to the x. Okay? It might be fun, actually, to go ahead and graph what would y equals 3 to the x look like. What would the difference be if we drew y equals 3 to the x on this same graph here? What if I try y equals 3 to the x? What's that going to look like? It's got this point, right? Like 1, 3. So if I look at y equals 3 to the x, what's its y-intercept? What's 3 to the 0? 1. It has the same y-intercept as this one, all right? And what if I look at minus 1 into 3 to the x? I get 3 to the minus 1, which is 1/3, right? And then I get a 9th. And then I get a 27th. All right, so basically 3 to the x is under 2 to the x for negative values. See that? It's under it. And then they cross at the y-intercept. And then for positive values, 3 to the x beats 2 to the x. All right? See that? So there's your 3 to the x. What I'm trying to say is that 2 to the x is less than 3 to the x for x positive, right? Whereas 2 to the x is greater than 3 to the x for x negative. All right? Make sense? Now, do I need to draw more, or is this like enough? That's good. What's going to happen if I look at like 10 to the x? What's that going to do? It's going to go up even steeper, right? Yeah. Kinda.
Because it would be more flat on the negative side.
Ah.
Steep on the positive side.
Let's see here. What if we look at, let's see here, what else can I tell you? I guess the question is, I mean, it's easy enough to calculate the values of 2 to the x for something like, what would, for example, in between 1 and 2, you'd have what? You'd have like, 3.5. I mean 1.5, right? We have 1.5 to the 2 to the 1.5 power. What is 2 to the 1.5 power? What does that even mean? You guys understand 2 to the 2 or 2 to the 3? That makes sense, right? 2 times 2 or 2 times 2 times 2. What does 2 to the 1.5 mean? Well, 2 to the 1.5, we could understand that as 2 to the 3 halves And that's easy enough to understand. That's really 2 to the 3 to the 1/2, or if you like, the square root of 8, right? And the square root of 8, if you simplify it, it's 2 root 2, which is approximately 2.8-ish. So to a good approximation, this is 1.5 comma 2.8, right? So it's not halfway between 4 and 1, is it? What's halfway between 4 and 1? $2.5-ish? Yeah, 4 minus 1 is 3. 3 divided by 2 is 1.5. So if I do 1 plus 1.5, it's what? Wait a minute. Oh, come on, guys, don't let me do that. Good grief. Oh, sadness. Infinite sadness. You barely know what I'm doing. Yeah, well, that is apparent at the moment. Sorry, is this legit as a label for this point? No. No? What should that be? 2, 1, right? Oh, I did it again. 1, 2. See? 1, 2. So 1, 2. And if I did this right, this wouldn't be halfway between. This would be like a little bit lower. A little bit lower. See, because there's 2 units between here and here, right? And so like it's more like kind of down here. My point to you is, if you go, this is halfway, this 1.5 is halfway between 1 and 2, but see what happens is you go 0.8 going from here to here, but you're actually going more like 1.2 from here to here. See, that's the way the exponential function works, is if you go over the same amount, as you go from left to right, you're going up more and more and more for a given like displacement. As you trace over the graph, it grows faster and faster and faster and faster as you go over, right? So it's not going to be like halfway. Anyway, that's all I was trying to get. So then you can ask the question, okay, so what does 2 to the pi mean? What would that even mean? See, pi is what? Yeah, 3.14151951970645528675309. What was it?
I'm double checking that.
You're double checking it? No, don't double check. It's true. There's nothing to see here. It's not like I'm just making up numbers past the 5th digit of pi because I can. Have we already covered this in here? Is there somebody here who's memorized pi? What's that? So you have more memorized. Very good. So I'm already being called out past this point as garbage, right? Is that right? Yeah. Because I just made it up. Fair enough. Because unless you have somebody like Mia or someone else who has like a high school algebra teacher who would make them memorize the digits for pi for extra credit or something, usually you can get away with making it up past about the 5th digit. But there is this like subcurrent of high school teachers who are teaching people more digits and ruining my thing. Not happy about this. Anyway, my point is, this is not a fraction. Pi is not a fraction, so I can't do like up here. See, if I have 2 to the m over n, I can interpret that as the nth root of 2 to the m. See, so any fractional power I can calculate as a root of a power, but not all numbers are like that, right? Pi is not like that. Pi is not a rational number. So what does 2 to the pi mean? That question I can't really answer in here, but the good news is you have a calculator. And so 2 to the pi is a few keystrokes away for us. So we turn on our calculator, we find 2, number 2, and yeah, you better get a calculator that can do this, otherwise this part of the course is really hard. Pi, 2 to the pi, and I calculate that, and it tells me that this is 8.8249778, whatever, da 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 da. That's an approximation, of course, but it also kind of makes sense if you look at the numbers that we have, right? If 2 to the, what is pi squared by the, well, excuse me, what is pi? Pi is what, 3.14? So notice it's a little bit bigger than our last thing in the table. So it makes sense that it's bigger than 8, right? It would be like about right there. So, any questions? So, listen, we do need a calculator to calculate certain powers, right? If it's not something nice like 2 to the 3 halves or something, we might need a calculator to calculate the exponential, all right? Yes?
Can we use our graphing calculator for like tests and stuff for this?
I said no graphing calculator on the test, though. Sorry. Unfortunately, if it was just me teaching college algebra, I might bend, but there are other sections which have this policy, which I'm like trying to be a good citizen of the math department and have the same policy, so. What? We're not in the math department? But you have to promise me that you wouldn't graph with the graphing calculator. Is that possible?
No, I wouldn't understand
Yeah.
I can say that.
We cannot do this. I'm sorry. It really, this kind of calculator is much better actually for this class because it does things like add fractions and solve quadratic equations. Like, what's that? Yeah, it has logs and stuff too. It is all of that. And also for like your, if you take a class in like chemistry or something, this actually has the fundamental constants built into it. It's got like the gravitational constant, the electron charge, mass of the proton, all that kind of stuff. There's like 40 different natural constants built into it. I think it'll also do like some amount of conversion things, like converting meters to feet and junk like that. I think if you, but those are, I'm not versed in that part of it, okay? Okay, so one of the things I wanted to point out to you guys is that there is a number between 2 and 3. Okay, so first of all, there is got to be some graph between these two, right? If you look at it, there's a graph in between these two. Well, that could be what? For instance, this could be what? Y equals to, you say 2.5, it could be y equals 2.5x. But let me try to explain what the green graph is more carefully. If we look at the blue one, all right, it goes from the point -1, 1/3 up to the point 1/3, right? Like that. And the red one, it goes from what? It goes from the point, -1, 1/2 up to the point 1, 2. I finally got that right? So if you approximate those with their secant line, right? What's the slope of the secant line? What is a secant line? Do you guys know? It's just connect the dots with a line, just that. That's the secant line, okay? What's the slope of the secant line here? So we have 3 minus 1/3 over 2. And this one, the slope for 3, the slope for 2, we've got 2 minus 1/2 over 2. So you guys tell me what those work out to. Oh, you already got me? Okay. Anybody? Nobody? That's 8/3 over 2, 8/6, 4/3, approximately 1.333 repeated. All right. The other one is 3/2 over 2, also known as 3/4. That's exactly 0.75. All right. The meaning of these slopes, like if you go back to my other picture, so essentially, if you want to, you could imagine if I took this line here, right? And if you imagine me just like shifting it down, so it just kind of just barely, so imagine taking that secant line and just kind of translating it down so it sort of like approximates. It's close to the function at the y-intercept, and likewise this one, imagine just kind of like moving it down here. So you can see how it would be close to the point 0, 1, right? It would be close to the point, it'd be a pretty good approximation to the exponential graph close to the y-intercept. That line with that slope, right? In other words, let me draw yet another picture. If I think about the 3 to the x graph, and if I think about the 2 to the x graph, right? Oh man, that was bad. I'll get it eventually. 2 to the x graph, right? If I look at the lines that are close to the graph, like here, for the red one, that would have a slope less than 1, right? Whereas if I look at the line which is close to the blue graph, this would be called what's called a tangent line. If I look at the tangent line, oh, I don't want to use green. If I look at the tangent line to the blue one, right, it would be more like this, and that would have a slope greater than 1. These calculations I did with the secant line illustrate that, because the slope of the secant line would be close to the slope of the tangent line. You can kind of see it if you look at it. So the slope of the slope of the 3 to the x function at the y-intercept is bigger than 1. The slope of the 2 to the x function at the y-intercept is less than 1. So if you think about it, there must be some choice of base between 2 and 3 where the tangent line to that one at the y-intercept, that would have a slope of 1. All right, so that is a special number. So basically this is it. If you have your exponential function looks like this, and the tangent line right here has slope 1, then this is not just any exponential function, this is the exponential function. So this is the exponential function. And it turns out that e is approximately 2.71, and I will behave. I will not just make up stuff. It's in your calculator, right? I can give you more digits if you plug it in. This is Euler's number, in honor of Euler, did a lot of things in the 18th century. Almost everything in this course, in some sense or another, he discovered or popularized in the way we're doing it, give or take, a lot of it. Yeah. So anyway, there's a special button in your calculator. Now, at this point, I think it would be helpful for us to graph a few more. Let me graph. Actually, I'm going to take a break from the graphing. We'll come back to the graphing. I want to stop. I'm trying to mix things up this semester a little bit and kind of not in the past, I've just done all of the graphing all at once and then come back and done all of the equation solving all at once. So what I'm trying this semester is to kind of mix it up a little bit and here's what the exponential function is, talk about what its graph looks like a little bit, but then talk about how to solve equations involving exponentials. So I'm trying to mix it up a little bit. So let's try to solve some of the equations. And the key there is the so-called one-to-one property. And what the one-to-one property say? It says if you have a to the a to the x equals to, well, a to the x1 equals to a to the x2, let's say, that tells me that x1 has to be equal to x2. That's the one-to-one property for the exponential. Why is that true? I mean, is this any different than what I said the other day? I don't think it really is it? Because I talked about one-to-one functions, remember? They have to pass the what? The horizontal line test. How about these graphs? Do they pass the horizontal line test? Oh yeah, they definitely do. All right. So with that in mind, we can do examples like example 2, if I had, for example, 2 to the 3x minus 1 is equal to 4, how could I solve that? Well, it's not quite the right format yet. I need to take the 4 and rewrite it as a power of 2. 4 is what? Yeah, 2 to the 2. And now I can use the one-to-one property. The one-to-one property here tells me that 3x minus 1 is equal to 2, right? Lo and behold, 3x is equal to 3. X is equal to 1. Congratulations, you solved your first exponential equation. Woohoo! Actually, that's probably not true. You probably solved some in high school. Almost without a doubt, right? But it's been a minute since you solved these, right? Example 2. How about this one? Example 3. What if we have 3 to the x squared is equal to 1 over 81? What is 81?
It's
9 times 9, right?
yeah.
Which is 3 squared times 3 squared, right? Which is 3 to the 4th, which is 3 to the minus 4, right? Ooh. This one's kind of funny, isn't it? If the one-to-one property here would tell us what? X squared equals what? Negative 4. Ooh. So no solution. I would say in retrospect that's kind of not surprising because x squared is what? X squared is greater than or equal to 0, right? So think about the graph of 3 to the x. If you have something greater than or equal to 0, what happens to the 3 to the x graph? Well, you're over here, right? You're bigger than 1. So there's no hope that you can get 1 over 81 from that, right? Let me salvage this example. Example 4, what if we had 3 to the 7x minus 1 equals to 1 over 81? Ah, well now we can do it, right? So now we can have this is equal to 3 to the minus 4, which gives us then, by the one-to-one property, that 7x minus 1 is equal to minus 4. Isolate our x. 7x is equal to minus 3. X is equal to minus 3/7. Nothing wrong with having a negative x here. It's just that we couldn't solve x squared equal to a negative number unless we use complex numbers, right? But if you guys wouldn't agree to let me teach calculus, you're not going to agree to let me teach you complex analysis either, right? Yeah, fine. I'm just joking. Let's keep it real. So, any questions? So basically the one-to-one property allows us to equate exponents and then go from there. But in order for this to work right now, we have to have the same base for both sides. Like if I had something like 2 to the 3x equals to, 3 to the 7x or something like that, I wouldn't know what to do yet. We'll learn how to solve those later. At the moment, we have to have the same base for both sides for this to work out, all right? So now that we've covered that, let's talk a little bit more about graphing exponentials. So what else might you run across? What if the base was like a fraction? What if the base was like a half? What would that look like? Do you guys know? Let's think about that. Let's try graphing 1/2 to the x. So, example 5, y equals 1/2 to the x. So let me point something out to you. This is really 2 to the minus 1 to the x, right? Which we could trade for 2 to the minus x. Now hold on a second. We know what to do. Now we know what to do, right? Because we already know that if we have a graph like 2 to the x, right? If this is 2 to the x, that's 2 to the x, then what does y equals 2 to the minus x look like? What's the situation there? It does what? We reflect over the y-axis, right? If we replace x with minus x, we just reflect mirror image like this. So there you go. That's what y equals 1/2 to the x looks like, just like that. So for both of these, what's the horizontal asymptote? Yeah, I heard 0. It's a little different here, though, isn't it? Because notice that we could write this. We could say, 2 to the x goes to 0 as x goes to minus infinity, whereas 1/2 to the x goes to 0 as x goes to infinity. Okay. That's a nice shorthand to express that idea. On the other hand, that's only one-sided, right? On the other side, what happens to 2 to the x as x goes to infinity? It just blows up, right? It goes to infinity itself, and vice versa. The 1/2 to the x gets super huge for x negative, right? So, unlike the rational functions we looked at, the graphs there, what happened? It behaved the same, both at plus and minus infinity, right? They both either went to 0 or they both went to 2, but they behave the same on both sides for the examples we looked at. Setting aside that one weird example I did to start with, but anyway. Any questions? So how about this? If I ask you guys to graph, what if I said graph, y is equal to 3 plus 2 to the x minus 1. What would that look like? What do? You take your y equals 2 to the x graph, right? You shift it up 3, right? And you move it to the right 1. So its graph would look basically just like this. 3. And basically we just take this one and we move it up to here, and we shift it over 1. I haven't been very faithful with my scale, but something like this. So that point would be like 0, 3.5. This point right here would be 1, 4. And you can go on from there. So we can play the same games we did before about translation, like shifting horizontally and vertically. We can do all those things, and we can mess with exponential graphs and make new exponential graphs, right? But unless I say otherwise, when I talk about an exponential graph, I'm literally talking about y equals a to the x, okay? Although the people would say things like it wouldn't be unusual, guys, to have somebody say y is equal to like a constant times a to the x plus another constant. Like to say something like that sort of formula was an exponential function, but I would say it's kind of an exponential type function. I don't know. The language here is not entirely precise. All right? Any questions? No? So moving on here. Question. So we agree that these are all one-to-one functions, right? What's the domain of the exponential? What's the range of the exponential? I'm going to erase this here if that's okay with you guys. So if the exponential is a one-to-one function, what does that mean we can do? we can invert it, right? We can find the inverse function. Yeah? So, my point to you at the moment is that the domain of the function is everything, right? And the range, what is it? What's that? Well, what's the range for both of these? Oh yeah, fair enough. Not example 6, but example 5. 0 to infinity. Now, yeah, fair enough. Down here, it's different, right? Down here, we'd have, if this is equal to f of x, the range of this one is what? 3 to infinity, and the domain? Everything, right? Yeah, everything. Fair enough. Did you get that? I'm sorry, giving you a workout. Although, I don't know. What sport would this workout be useful for? I'm not sure. Miniature arm wrestling, maybe? I don't know, but I don't know. It's gotta be something. Maybe like endurance videography. Is that a sport? Like should be a sport? Why not? Olympic sport? No, that would ruin it. If it became an Olympic sport, that would ruin it. Once something goes to the Olympics, forget about it. So, if this is a one-to-one function, and that's its domain, and that's its range, we can define an inverse function, right? So let's do that. Definition. The inverse to f of x equals a to the x is the log base a denoted, I'll write it down here, f inverse of y, let's say, is equal to log base a of y. Of course, you could put an x here and here. The reason I'm putting the y is just to play the following game, okay? And how is it defined? Log base a of y is equal to x only if and only if a to the x is equal to y. All right. That's some people like to think of it in this way. In other words, to solve this, to figure out what the log is, you ask the question, okay, well, a to what power gives me the y? It's kind of backwards. I also prefer a sort of more mechanical way of thinking about this, which is given to us by the following two equations. And here they are. Well, on the one hand, we have that log base a of a to the x is equal to x for any real x. All right? On the other hand, we have that a to the log base a of y is equal to y for any for y positive. So we can, why is this? What's the domain? What's the domain of the logarithm? It is 0 to infinity. Why? Because it has to be equal to the range of the function. So we can only input positive numbers into logs. All right? So the log is the inverse of the exponential. Let's actually calculate a couple. So example 7. So you guys help me out here. What would log base 2 of, I don't know, 32 be equal to? So what's the game we want to play here? Well, you'd be like, well, I've got a calculator that I spent $20 on, and I'm intending to use it, or 15, or I don't know, well, you borrowed it from a friend, whatever. Anyway, this calculator, it will calculate log base 2 somehow or another. Actually, I'm not sure. I think it's in there somewhere. I actually never use that because there's another way to do it, which I'll show you next class. But This one we don't need the calculator for because this one we can use the basic definition for. This is log base 2 of what? 2 to what power? What's 32? 2 times 2 is 4. Right? There's 2 of them. Times 2. 4 times 2 is 8. 8 times 2? 16 times 2? 32. 32 is 2 to the power 5. 2 to the 5. Aha! Therefore, this is equal to 5. All right? Why is log base 2 of 32 equal to 5? That is true because 2 to the 5th is equal to 32. Yeah.
Could you also write the log as an exponential?
Oh, we will do that, but we're not there yet. Isn't that what I did? Or, well, example 8. What if I had, log base 3 of, 1 over 27? How would I do that? I go, well, that's log base 3. 27 is 3 times 3 times 3, right? 3 3's multiplied together. That's 3 to the minus 3, actually. Okay? That's 3 to the minus 3. So once we have that pattern, log base 3 of 3 to the something, then that gives us whatever the something is, in this case, minus 3. So, listen, we're going to spend the next 2 weeks or so, I think, just on logs and exponentials, how to solve equations with logs and exponentials. Sometimes I take a lot longer to introduce this, but I thought I'd just, be somewhat Machiavellian in this lecture and do my evil all at once. Introduce this because this is what you need to learn. And I've tried to put a lot of daylight between this lecture and the final. So you should have time to learn what the log is and get used to it so that when the final comes, we can all do well, pass, go on, right?
I appreciate that so much.
Yeah. I really do try to, there should be a little bit of a buffer between the last test and final in here, hopefully. Anyway, thanks guys.